Hi, ladies and gentlemen. This is Mr. Green again, and this is Unit 2, and we're going to be talking about things that we can use in proofs. Okay? So the other day we were talking about using definitions in proofs. Well, we are going to be talking about some other things that we can use in proofs today. Okay? So where should you all be? I don't want to hear that anyone's still working on Unit 1. I've gone through and I've been grading away like a little madman, but you need to make certain you got everything turned in Unit 1. We do not want to have any zeros being in there permanently. So let's get rid of all those zeros. Make certain they all get made up. Don't forget, quiz corrections, half credit. Yes, on a unit exam, there were 5-point questions. That means you get 2.5 points for every one you correct. Yes, go correct that Unit 1 exam that you didn't do good on. Just can't correct the Part 2. Okay? So here we go. What can we use in proofs? The addition property of equality. Now there is one I've never heard of before. If I take A plus B and I say that A is equal to B, then I take A plus C and I say that B plus C is equal to it. What did I do? I added C onto both sides of the equation. Have you ever seen this before? Why, sure. In algebra, you use this all the time. You had 2x minus 7 equals 11, and you added 7 to both sides of the equation, right? And you got 2x equals 18. Guess what? You used the addition property of equality right there. All we're going to be doing in writing a proof is doing algebra statements and writing the reason that we took that step. It was the addition property of equality that says I could do that. That's how easy a proof really is. Don't make it any harder than it actually is. So here we go. Let's go to the next one. This is called the subtraction property of equality. When have we seen this one? 2x plus 18 equals 7. Well, I subtract 18 from both sides, and guess what I wind up with? 2x equals negative 11. Right? 2x equals negative 11. That was the subtraction property of equality. I subtracted the same amount from both sides. That's why I got that information. That is a reason in a proof, in an argument. So you notice I made a statement, and there's my reason for it. That easy. That's what we're doing, is we're looking at why we took something. Multiplication property of equality. These get kind of redundant, don't they? So if I have 2x is equal to 8, I say that if I multiply this side times 1/2 and multiply this side times 1/2, I multiplied the same amount by both sides. This becomes x equals 4. Multiplication property of equality. Wow, that's really easy. This one here says division property of equality. Note, there's a special condition on this one. You can't divide by 0. So it falls apart if we have division by 0. Don't do 0, okay? But it says that if I have 2x equal to 8, instead of multiplying times 1/2, if I divide by 2, I get that x is equal to 4. That is the division property of equality right there. Okay? It's not equal to 0, it's a 2. And if I divide both sides of the equal sign by it, I wind up with a valid statement at the end. Division property of equality. Okay? How closely related are the multiplication property and the division property? They are very closely related. Okay? The only difference is you can't divide by 0. Can you multiply by 0? Why, sure you can multiply by 0. Can you multiply by 1 over 0? No, because that is an invalid number. Okay? So you got to remember, you can use those two kind of interchangeably, but you do have to be able to recognize when you're multiplying and dividing. Okay, substitution property of equality. If A is equal to B, then I can substitute B anywhere I see an A. Where did we use this? Remember when we had those things that were two equations, 2x plus 3y equals 23, and then they'd have another equation down here and they'd say that x is equal to y plus 3, and you could take this y plus 3 and substitute it in for the x right there and come up with 2 times y plus 3 plus 3y equals 23. Remember doing that? That was called simultaneous equations, and you were solving two equations with two unknowns, and you were using substitution approach. That's what we're doing right here. We're substituting. We're putting one value in the place of another value, or one variable in the place of another variable, or a value in the place of a variable. We are just substituting it in. This is the one that the professional basketball teams use all the time. They substitute one player for another player. That is a substitution, and the substitution property of equality allows them to do that. Okay? Then we've got these others that just really kind of make people mad. This one is called the reflective property. You can always say that A is equal to A. Well, why in the world would you want to do that? Trust me. There are times when you want to say that A is equal to A. It will come up in a proof sometime, and you'll look at it and go, well, why am I wanting to do that? It's called the reflective property of equality. It's like looking in the mirror. If you see the same thing, it's your reflection. And guess what? Reflective property of equality. I'm trying to give you ways of remembering these properties, by the way, guys. The reflective property of congruence. What's the difference in equality and congruence? Equality has an equal sign. See the equal sign right here? Equal sign. Congruence has a congruent symbol right here. Just thinking for a second. What's the difference between them? Numbers are equal. Objects are congruent. Oh, that's the way it works, is it? Yes, that's the way it works. Anytime I've got two numbers, I can say they're equal. Anytime I've got two measurements, I can say they're equal. Anytime I've got two objects, a triangle and another triangle, I have to say they're congruent. Anytime I have two line segments, line segment A, line segment B, I have to say they're congruent, not equal, congruent. Even though their measures might be the same, they're still congruent. Okay? Then we look at what's the definition of congruence. It is the fact that their measures are equal. And we can switch from congruence to equal at that point, but that's a different story. Okay? Symmetric property of equality. Symmetric says that if you take A is equal to B, then you can take B is equal to A. This is one of those dyslexic formulas. A is equal to B, B is equal to A. They're swapping places all the time. That is symmetric property of equality. Okay? Last one here. I'm sorry, it's not the last one. Symmetric property of congruence. Same thing, but it's the objects this time. This time it's not the fact that the measures are the same in swapping position. It's the shells that are moving and switching positions. So if the shells are equal, then you can say they are congruent to each other. Transitive property. This is one I said was going to be last. If A is equal to B and B is equal to C, then A is equal to C. Well, look at this. Monkey in the middle. B, B. We're going to eliminate the monkey in the middle, and what do we got left? A is equal to C. That makes good sense, right? Well, that's all this is trying to say. It's called the transitive property of equality, and when I eliminate the monkey in the middle, it becomes the outsides are always equal to each other. Transitive property of congruence does the same thing. I'm going to eliminate the object in the middle and say that A is equal to C. How does this work? Well, this house is congruent to the house next door, and the house next door is congruent to the one down the block. Therefore, this house is congruent to the one down the block. We've all seen houses like that. They're all congruent to each other, right? That's exactly what you're doing. You're eliminating the house in the middle from the statement. You don't have to compare it any longer. You just go to the one at the end of the row. Okay. What are we doing here? We're developing awareness of structure of a mathematical systems, connecting definitions, postulates, and logical reasoning and theorems. We determine the validity of a conditional statement, its converse, inverse, and contrapositive. What are we really doing? I'm giving you objects that you can use in proofs. Okay? Why? When we get to looking at proofs, we need to know what we can use for the reasons. I've given you a couple of things. Definitions. You can definitely use a definition in a proof. I've told you can use these algebraic properties. You can definitely use algebraic properties in proofs. I've told you can use other theorems. You can definitely use other theorems inside of a proof as long as it's already been proven. Postulates. You can use postulates inside of theorems as long as everyone agrees that they are true. I'm giving you things you can use in the proofs for the reasons. Why am I making this step? Why am I doing this? I got to give it a reason. Okay? In algebra, you just had to show the work. In geometry, you show the work and then you give a reason why you're doing it. That's what it takes to make a formal proof. That's what it takes to do deductive reasoning. The difference between inductive and deductive. Inductive is just looking at observations. Deductive is proving it. And that's what we were getting to right here. Is we're getting to the point where we can start to write some proofs and look at some proofs. So, last slide always is tell me your section number. I still get lots of emails that don't have section numbers on them. I'm just trying to get you guys to make it so that we can find you quickly and communicate very effectively. So, making certain we get all the information. So, I will talk to you next time.